who dares to fight with the icon of his day, and she finds her own miracle on the way. I said, hey now, life's a joy. You gotta try your best and give your all, and when the facts don't fit the theory, change the facts again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. It's a beautiful day.
5, 4, 3, 2, 1. Silence.
Good morning, good afternoon, good evening, wherever you are in the world. You have reached Saturday Science Chats with the John Chappell Natural Philosophy Society and Dissident Science. Hello. Today we've got our special guest. Been trying to get him for months, but he has been very busy and actually working on spreading the news about his work, which is just great. We have Steve Bryant coming up. But before that, of course, we have all of our things we must talk about. And of course, again, you've reached Saturday Science Chats, and we are sponsored by the John Chappell Natural Philosophy Society. It's been around for about 3 decades now, and Dissident Science, my YouTube channel, and things are growing actually, which is really great. Today, of course, we are going to be speaking with Stephen Bryant, one of the brilliant young minds. I'm going to give him young mind. You notice what I said? See there, young mind of critical thinkers outside of mainstream. If you haven't gotten his book, it is a fantastic book. You got to get it. Disruptive. I got it here right myself. Got a copy. He wrote something very nice into it. And we're going to be talking with him after all of our announcements and opening intro here. So you don't want to miss that. He's going to have a great presentation. He's a very elegant speaker. Of course, I do want to thank everybody who joins us and watches this also in recordings and supports our organizations, both John Chappell Natural Philosophy Society and the Dissident Science, because without you guys, we wouldn't be here. This is an endeavor of organization and lots of individuals, literally probably over 10,000 dissident scientists around the world who are working very honestly and critically, not afraid to take on mainstream and look for truth, because that's, in the end, that's what we're trying to do. And of course, we know that doesn't happen in mainstream science very much. You can't challenge Einstein if you want to get your physics degree, something like that. But of course, without all of you, this would not happen. Of course, this is where critical thinkers meet. We are the John Chappell Natural Philosophy Society. It was started as the MPA, Natural Philosophy Alliance, back in the early 1990s, and we've evolved over the years, and we have our new name after the guy who founded the organization, John Chappell, and we keep going worldwide. We have our, of course, conference coming up. We'll talk about that, and our mission is to be an organization that, above all, promotes critical thinking without malice. That is, if you think the Big Bang is wrong, come on and talk about it. We listen to everything because that's the way science should be. After all, we're free to think about what we want to think about, and we can think something is wrong and show ourselves that we believe something's very wrong in mainstream science. And a lot of people do. But there's not very many people who support that, and that's what we do. And we we are an organization that supports, publishes, and promotes serious scientific work outside of mainstream science. Yes, serious work, to provide a forum to open debate about modern topics in physics, cosmology, philosophy, mathematics, and more. And to provide a forum for presenting serious papers and theories without fear of censorship. We have our, for instance, our conference coming up. It's going to be virtual, of course, this year, and to be run and controlled entirely by our paying members. Who are we? Well, we're open to challenging mainstream science. We allow and encouraging competing ideas or models. Heaven forbid that science be exactly like software. Of course, my guest today knows a lot about that. It's very strange, isn't it, how software engineering, it's great to be disruptive, but you can't be disruptive in physics. But that's exactly what we're going to do today, so don't go away. Right after these announcements and information. We also follow the scientific method. A lot of people think just because we work outside the mainstream that people throw away. It's how do you say, it's a stereotype of people who challenge any type of dogma. And of course, it's absolutely not true. In fact, what we find mostly is that we follow the scientific method, and science and mainstream science does not, because if they did, they'd have to admit a lot of things were wrong. And we can consider an idea without accepting it, just like Aristotle says. And that's what I always encourage you guys to do. We're going to have speakers. We've got a couple more speakers lined up, and you got to keep an open mind, folks. That's what I try to do, and everybody should try to do. And we give voice to the voiceless, because a lot of these people don't have a place to talk. And this is, of course, where science advances. It never advances inside mainstream. It's always outside the mainstream. What we are not a specific point of view. Right? We don't all believe in one kind of theory or idea. We're not a general science organization, so you're not going to see videos or people. I'm going to bring on people and talk about how magnets work. We may bring somebody on and talk about what a magnetic field is, which is, of course, no one seems to want to care about, but numbers of us do, Unel Denu in particular. We're not sort of a new age, or we're not conspiracy or UFO. We really want to stick to foundational science, light and gravity and fields, magnetism, tectonics, math, philosophy, Big Bang, cosmology, because there's so many problems there. Let's start there. Let's not get into things that, we got to start with basic and foundational science first. We do have some websites which you can check out. Our online magazine, that is, if you just wandered in here and wonder what the heck this is all about, and that what are you talking about, mainstream science it got problems with it. Well, just go to beyondmainstream.org and you will find there, click on problems. And you will click on problems like relativity. Oh, there's problems with it. Yep, click on that. And you'll see articles and papers that have to do with that. And I think there's over 2,000 papers we have cataloged about problems with relativity. It's the most disputed theory on the planet, without a doubt. Of course, if you talk to mainstream, they won't say that, but that's a different story. Naturalphilosophy.org is where you can go to become a member of our group. You don't have to be a paying member. You can just join in. You register there. We require you use your own name. It's not like not anonymous type of thing where people go in, and so you won't be fearful about who you're talking with in discussions. And we have all kinds of groups on gravity, on ether, on expansion tectonics, on philosophy, et cetera, and you can join the group, and you can become a member and help support this. And we do have a natural philosophy Wikipedia based on the same software as Wikipedia, which is Wikimedia. I think it's called Media Wiki or Media something. I can't remember now. How come when I'm on the air, I forget everything? So, but anyways, it's the exact same software as Wikipedia, except ours is closed because we allow people to go in there. If you're a member of the CMPS and you want to put your bio in there as if it should be on Wikipedia, which it probably should, then you can do so, put your papers, all the kinds of things. And we have over 10,000 pages collected since 2008. So there's quite a lot of information there. You can check that out. And of course, we do have memberships, because without your memberships, we do not survive. And we got quite a few expenses to do all this stuff today to keep our website, our server from not being attacked and hacked, which we had problems for literally 3 years with that, because people don't like us shaking the tree or upending the apple cart. Then we have to even pay a security company to keep our servers running really well. And we try to keep all the expenses down, but it's a couple $1,000s. So any donations appreciated. Monthly, we have people who are monthly at 5, 10, 15, 5, 10, 25, 50. We do have all of those, and we have annual memberships, and we of course get donations. And I do want to thank our patrons, Nick Percival, Dr. Cynthia Whitney Ramsey, pen name from, he's got his book out actually, and all the annual and monthly memberships. Of course, we do need your vital support, so please, and if you're watching this and you like this channel and you like these broadcasts that we do, no matter if it's Dissident Science, CMPS, or even on Facebook, hit the like button, hit the subscribe button, and actually, I think we're coming in on 1,000 subscribers for the CMPS. Before we started all this new modern stuff, we had 127 people, I think, subscribed to our YouTube channel. It's got a lot of great videos on it. But now we're closing in on 1,000, and we're closing in on 4,000 on Dissonant Science. So I want to thank you. But again, if you like this, subscribe, hit the little bell so you can be reminded when you'll see when we come on live. And your support is greatly appreciated. And if you can become a monthly or annual member, it really is important. Of course, we're looking October timeframe. Probably is going to be more like the November. Again, I've been busy, and I apologize for everybody. But my father and I literally launched our book just a weekend ago. Oh my gosh, it's just that quick. It's not been that long ago. It seems a lot longer. And so I've been involved with like that. Anybody who knows, you've been 30 years in this field, and I never wrote a book actually, and it took us 6 years to write this one. So I've been busy. I do have a page up. I do have that, but it's going to be beyond mainstream, but we're going to get more of a specific theme. I've got the people who help me out with the conferences, and very soon we'll have the page where you can register, etc. And I'm probably talking about something I already have a slide on, probably. But again, it's going to be beyond mainstream science with a specific and those theme, and those people who do attend virtually you'll get a T-shirt, you'll get a credential, and then the proceedings will be available, but everybody will have to buy those on their own, and it'll be available worldwide on Amazon, and we'll do that ahead of time, at least about 3 weeks ahead of time, so that they will be available and so everybody can purchase them before that. And again, probably more in November now, but I'm looking to do Thursday, Friday, Saturday, and Sunday, full days in the U.S., and that'll allow us, for people who can't during the week, to have some time to be able to watch and be live as well. The speakers will record a presentation. The attendees can join in Zoom discussions. Those Zoom discussions will only be available to those people who do pay for attending, and both of those will receive a T-shirt and credentials mailed to them. If you are international, we have to add $50 to get that mailed to you. If you do so, I do want to have those. We do have proceedings are open, and we are receiving. People are sending their papers. We're lining them up. So and again, the conference proceedings will be available on Amazon worldwide. Oops. CMP Publishing. We are now fully published. Notfinity, Matter in Motion, is available on Amazon. Published and available also is Ether. He spelled it E-T-H-E-R. Of course, he's really meaning the ether that's out there supposedly for the medium for transmission of light. And that's actually available free. And we just published, you can go on worldwide. Our book is for sale worldwide. I did check it on from Japan to Europe to France, the United States, to Canada, to Australia as well. We put it at the lowest amount. I think we make a couple bucks on the book, but that's also available. And again, you can go and get this book, 400 pages in PDF form, to theetherbyramsey.com, and that's available. It is and was helped by the CMPS to publish. And you can take a look at that. Hopefully we'll have a presentation on that. And if you do take it for free, the author, who is a friend of mine, who I do know, he asked you if you could make a donation to the CMPS, $5, $10, 20, whatever. That would be great. Any proceeds would go to us. And he is also a sponsor, a patron of our organization. Greatly appreciated. Thank you so much, Ramsey. And of course, Notfinity, Process, Matter in Motion, is available by George Coyne. If you haven't seen our interview with him, actually, I think we have 2 now. This is the 2nd edition, and here's his cover. Again, helped and published by the John Chappell Natural Philosophy Society. publishing. We just help people out getting it out there and that kind of stuff. So, and another absolutely great, phenomenal happening is Dr. James Maxwell. It's really hard to get your book published around the world. So he is actually giving it out for free. And for those who don't know, in my opinion, Dr. James Maxwell is the most important geologist of all time, in my opinion. This book is absolutely like 100 dissertations, PhD dissertations in one book by one person. We've been fighting out. There's actually a geologist Facebook page with over 100, almost 120,000 people. And we go out there and I put something about this and I say, hey, this book's available. And a lot of people have been interested in downloading it. So we are getting this out there. And believe it or not, social media is helping. And it was interesting, just a quick story with that is I put it out there and I was talking about it and there was some discussion about it. And then, of course, you get these people who are trolls, as we call them. What is a troll? Is a person on social media who goes out there and their job is just to kick you. Just like they're going to go kick a dog or key a car. Their goal is just to make people mad and treat them like trash. And of course, somebody was doing that, and so they put in a comment. It says, "Oh, I haven't heard anything." One of the posts. So you can go in there if you like geology. You can post. I post things about tectonics in a way that's not too aggressive and telling everybody that they're stupid. Nothing like that. Just, hey, check this out. And so somebody puts out a post and it says, "Oh, I haven't heard a post from the expansion tectonics people. Oh, wow, that's so bad." So I told the moderator, I said, "Hey, moderator, this isn't the way you treat science." And I was going to think, okay, will this group actually hold up into the ability of being civil and coming and allowing new ideas? And sure enough, they booted that guy. And so we're out there. So I publish now and then when I can. And if you're out in social media and see something, make a comment. Don't be attacking, but make a comment. You bring one person toward this and we all do that. We bring more and more people. And that's how it works, sort of grassroots. So again, you should try that. And our Principia Mathematica 2 is published on Amazon. Our ebook is coming. Believe it or not, ebook format is not so easy if you do it like what we did in LaTeX and Overleaf. Ours is, we have automatic generated stuff like index and all that stuff. So we actually have a company that's doing that, and shortly we'll have an ebook. I think the price in the United States is $35. It's only a couple above what we can, we can't make it almost any cheaper than that. And it is over 250 pages and it's color all the way through. So that's not bad. We do have books for sale on our site as well. So if you want us to say hello, sign something, say to you, autograph book, we'll send it to you. We also have T-shirts and hats available. And I'm sure everybody's like clamoring. I'm kidding. Anyways, it is out there. And this is covers. And the top is, I love this. I just came up with this probably about a month ago. I was talking to my dad, and the universe is not magic. That's pretty much what our book is about. And we did give a presentation about the book, and it was really well received to friends and family. So I had to talk to people who don't even care about science. And it turned out really well. I was really, really surprised. People came up to me and said, "I can't look at the universe the same anymore. I can't look at light, what light is. I can't look what magnetism is." So it was great fun, a great party. My dad turned 84 young. And how many people do you know who are 84 has a YouTube channel? It's coming up on 500 members. Hey, subscribers, remember, support all the people who are out there. Even if you don't agree with them, we got to support each other, folks. You may not agree. You can laugh at the idea that light is waves of particles. And you think it's ether, great. But please, just support each other. Anybody who I know who has a YouTube channel, anybody who has a Facebook page, whatever it is, I like it, I subscribe. It does help, because the more people, the more eyeballs you get on these things, the more likes, the more people it'll be exposed to through the algorithms. And we do have somebody coming up. This is Nick Percival, knows this guy, Mike Gimbel. He's going to talk about the aquatic ape, presenting evidence for that. So again, we try to go off a little bit off the physics and cosmology once in a while. You want to check that up. That's already set the date, September 4th. Of course, we are going to be talking, and we don't have a date yet for that, but we'll be talking about our book coming up as well. And of course, you can be next if you are a person that has something to say to the world. No one's listening to you. You are serious about what you're doing. We are a forum for that. So always welcome. Or if you have somebody you know that you think should be here, please just drop us an email. Send it to me, David at naturalphilosophy.org, or David at dissidentscience.com, or David at thehillstreet.com, or the other 100 emails that come my way. So if you have suggestions, that'd be great. Oh, play today's bumper. Oh, wait a minute. I think actually I have two to play, because I should have put one in there for coming. This is the coming one, when it should have been shown earlier. Hey, I just said that. Sorry, guys. I got to put those in. If I don't play today's bumper, then it doesn't happen. So now I will play today's bumper. Yeah, today we'll be talking. I'll give you a little background before he comes on. Instead of asking him about it, I will flatter him without him being around. So then I can say whatever I want. No. Today we are going to be talking with the author of Disruptive, Rewriting the Rules of Physics, Stephen Bryant. Stephen Bryant is super articulate. I would say of every person that I've ever seen since 1996 get up and talk, I felt like this guy really knew how to talk. It'll be a treat today. Very, very articulate guy. And of course, he is an author, a technologist, futurist, researcher, who investigates innovative applications, strategic implications of science and technology on society and business. So he has got his mind in what science and technology is. He is the author of Disruptive, Rewriting the Rules of Physics, which is a thought-provoking book that introduces modern mechanics, a unified model of motion that is not only more accurate than Einstein's theory of relativity, but will fundamentally change how we view modern physics. Stephen is a subject matter leader in the relativity community of the NPA and now the CMPS. He has published several papers on relativity and has spoken at the American Association of the Advancement of Science and as CMPS and NPA conferences and universities across the United States. He's passionate about science and technology. He is an active researcher and blogger, where today he's often found writing about the impact of implications of artificial intelligence, augmented reality on business and society. Oh, I do know artificial intelligence. That's my area. I work with human language, but he's looking at the implications on society. Stephen began his career in technology, joining Science Applications International Corporation's software engineering team after completing a Bachelor of Science in Computer Science and Psychology. Boy, that's a different combination. And completing his MBA. Man alive, this guy is well-rounded. Stephen joined Accenture, where he was able to pursue a mastery in two areas, technology and business. Stephen remained in consulting until joining Wells Fargo, where he's a senior vice president responsible for delivering large strategic initiatives. A lifelong learner, Steve is a computer science graduate student at Georgia Institute of Tech. Really? You're kidding. I didn't know that, Steve, because, wow. Because our company actually works with those in our I'm in the supercomputing department, and where he specializes in artificial and interactive intelligence machine learning. No, come on. What's going on here? Let me pull this down and bring him up. Hey, Steve, how are you?
David, good to see you. Can you hear me okay?
Yeah, I can. Where are you located? You're not in California anymore?
No, I'm still in California.
Okay,
Georgia Tech has a what they call their online program. They have a couple of degree programs in analytics, cyber security, and the first one that they launched was the Online Master of Science in Computer Science, which is a program that I'm a part of.
Wow, because we when we have our conferences, they're normally held in Alpharetta, Georgia, and I was at the conference, well, whenever the last one was, when we could be in person there. And again, I'm part of the supercomputing research group of LexisNexis, and I went across the street and I go, what are these bees doing here? And it was like it's like Georgia Tech. Oh, Georgia, yeah, okay. And then we had speakers from there. They were actually playing into sports, or maybe I got that wrong. But anyways, it was quite. So look at the overlap. It's great. So tell us before we go, I want to know one question, and that is, how did you come to disrupt physics? Why? I mean, look at your background. Why would you do that? Before you talk, I want to tell the audience how you got to writing this book.
Well, it's kind of an interesting story. When I was working at Accenture and then Primitive Logic, so two consulting firms, colleagues and I would sit around at lunch and we would brainstorm different ideas for inventions or companies and things of that nature. And one day I think we were talking about faster than light communications, and someone said, you can't do that. And I said, why not? Because Einstein said you can't go faster than the speed of light. I said, well, why does he get to make the rules? And they basically said, well, Steve, you need to go learn something about relativity, which I did. So I took a relativity course, started to drink the Kool-Aid, as the saying goes. But I have a nasty habit, which is I have to derive the equations myself to own them and internalize them. And as I went through that process, I found an anomaly, and down the rabbit hole I slid, and eventually found it's taken a while to be able to completely articulate what the problems are and the corrections, and a large part of that is what we'll walk through today.
Wow. Well, that's interesting. So you did go down a rabbit hole, but it's very fruitful. And so it ended up. When did you publish this book? When did it come out?
Oh boy, I think the book came out. I forget the year. I want to say it was 16 or 18. I think it was one of those years. It took about 2 years to write, and a lot of support from my wife and friends and colleagues. My daughter helped with some illustration. I had a fantastic editor, Grant Dexter, who really, his role was as the first reader, right? And so he was the representative of the reading community. So the mistakes that you see, when you find any in the book, just recognize that there were many, many, many more that Grant helped me to figure out, catch, or just say in clearer ways. And I really appreciate the partnership that he took with me on the work and on the project.
Yeah, and you also have the support of one of the great scientists of our generation, of all time, in my opinion, is Glenn Borchert.
Yeah.
So if you can get Glenn Borchert on board, that's something. So, okay, so you have a presentation today, so I am going to step aside, and what we'll do is I'll be watching the chat and stuff. So we're going to have Steve's going to give a presentation, and then we'll open it up to questions and discussions. So let me get myself out of here and get you and your slides.
Okay. Thank you, David. I'll go ahead and get started. So good morning, good afternoon, wherever you happen to be. My name is Stephen Bryant, and I'm going to walk through a presentation that I've entitled Top 10 Insights That Disrupt Modern Physics. I anticipate this talk will take about half an hour. I'm going to try and keep a lot of the conversation at the conceptual level. So if you don't have a lot of understanding of math, don't worry. There will be some equations. I don't want you to be worried about that, because we are going to take a look at Einstein's work as well. But we will keep things at a conceptual level. So ideally, our conversation today will be accessible to everyone. I will not be monitoring the chat window, because I will keep one window up so that I can see David's messages. So if there are questions, we will entertain those at the end. David's already given me a fantastic introduction, but I thought I'd just introduce myself a little bit here. My name's Steve Bryant, and I work by day in two roles. One is I work in financial services, where I lead a team that does intelligent automation, and we're starting to do a little bit more in artificial intelligence. Also, at Georgia Tech, I'm a graduate teaching assistant for one of their machine learning classes. So that gives me a chance to really hone my skill in terms of developing some deeper machine learning knowledge, because I have to be able to answer student questions and be able to really intuit what they're asking and what the material is. In terms of my education, as David mentioned, I'm actually completing my master's in computer science, emphasizing artificial intelligence. If all goes to plan, I'll graduate from Georgia Tech in December, so 4 short months. So I'm looking forward to that. And actually going out to Georgia and walking through the ceremony. That should be fun. I also have an MBA from the University of San Diego and a BS in computer science from San Diego State University. I like to do research. That's part of who I am. It's part of my passion. And I do research in a few different areas. One is physics, and you'll see some of that research today. The other areas are technology related. So artificial general intelligence and AI frameworks, that's some of the work and research I've had an opportunity to do at Georgia Tech. And also, most recently, technology and artificial intelligence, and using those tools as ways of mediating wealth inequality. So that's given some teeth to the technology research that I'm doing, and has been a lot of fun to get into. So let's talk about today, and what will we get out of today? There's really 4 goals for today, and if all goes to plan, and you'll be the judge at the end of our conversation, we'll hit these 4 goals. The first is I'd like to introduce to each of you a phrase that's easy to remember, that clearly states what the mistake is in Einstein's work and why it invalidates relativity theory. It's a very short phrase, but it's one that I hope that you remember. And ideally, regardless of whether you accept my work in my alternative theory called modern mechanics, or perhaps you have your own model and own ideas of something that might not be right with Einstein's work, you'll be able to add this messaging to your tool chest. Well, if there is a mistake, there's a natural question that flows, which is, how could a mistake go undetected for 100 years? So we need to answer that question. And that leads to another question, which is, well, Einstein's theory has been out there for 100 years. No one's found a mistake. And more importantly, there's a lot of experiments that seem to support it. So why is that the case? So we'll talk about that. And we will also introduce modern mechanics, which is my alternative theory of moving systems. It's built on classical mechanics, and it will become the framework for us to have our conversation and answer many of these questions. So the first one, though, I want to answer pretty quickly. In fact, we'll start to answer it on the very next slide, which is Einstein says 1 equals 0. And it's actually fairly easy to develop a proof that shows that 1 equals 0 is a false statement. So when we look at this, we can say, well, where does Einstein say 1 equals 0? I've looked at his paper. I don't see it anywhere. And what we have to do is we have to first explain the idea of an abstract case and a concrete case. Now, before I go too far, we are going to look at math, but I really want you to look at what they look like, not so much worry about the Greek characters. We have 2 Greek characters on this page. We have psi and we have tau. Psi looks like the cursive E, and tau is next to the C symbol. And it looks like, I don't know, maybe an R. So Xi and Tau, they're just Greek letters. And if you're not comfortable with Greek letters yet, I know many people watching today are, just think of them as 2 extra letters that we've tacked on to the end of the alphabet. So A, B, C, D, E, F, G, go to Z, and then add these 2 letters. So nothing magical about them. What we're showing here is Einstein's derivation from section 3 of his 1905 paper. And what I want to come to is this point that is number 1, because this is a very important statement. This is where Einstein actually creates Xi. It's a statement of creation. And in mathematics, when we have a statement of creation and it's a statement of equality, which is what this is, this relationship must always be maintained. It's not only true on Mondays, it's not only true sometimes, it's not only true when it's convenient for us. It is always true. So we can test this. I'm saying Einstein says 1 equals 0. We can put this to the test. However, there's a problem with our putting this immediately to the test, which is we don't get to directly specify xi or tau. Those aren't one of the variables that we get to state. But there are some variables that we do get to state. And Einstein tells us what they are, and they are x, y, and z, and velocity v, and time t. So we can use any combination of those variables and give them concrete values. We don't need y and z for our conversation today. So you can see over here, we're just going to look at x, v, and t. So this leads us to a question. Is there some way for us to use x, v, and t and put them into some equations and put this to the test? And the answer is yes, because Einstein gives us the transformation equations that convert our x's, our v's, and our t's into tau and xi. Okay, so we have what we need to go from an abstract case to a concrete case, which we'll do here. And we'll work our way backwards. So we're going to start by trying to solve for xi, which we'll do over here. And we have some terms. We're going to use x equals 1, v equals 0, t equals 0. I've picked those values because they're easy and we don't need a calculator to see what's going on. So we just do simple substitution from algebra. X becomes 1, v becomes 0, t becomes 0. We solve this equation, we get 1 minus 0. There is a beta term here, but from Einstein's equations, we can see we have this equation. He tells us what beta is. We've set v to be 0, so this becomes 1 over the square root of 1, which is simply 1. So beta is 1, so we can basically ignore that for the rest of our conversation today. So we get psi equals 1 on this side. How about on the other side? Again, Einstein tells us what this equation is. We come over here, we say t equals 0, v equals 0. Well, anything times 0 is going to be 0, so this becomes 0. So we get 0 minus 0, beta doesn't matter, we get tau equals 0. You feed those into the equation, we have 1 equals 0. So it's a fairly easy proof to show by using a concrete example. In this particular case, I've picked variables where it will be the case that 1 equals 0. And again, that should not happen because we know the statement of creation. This statement should always be true. And we found a case where it is not. But that takes us very quickly to the first insight that I wanted to share with you. And we have 10 of them, so I'm glad we got to the first one rather quickly. And that is, Einstein says 1 equals 0, which is mathematically incorrect and invalidates relativity theory. That's the key message. If someone wants to say, okay, I've got the key message from today, this would be the key message. But I'm hoping that now you want to stick around a little bit more because this should raise a number of questions. And basically, when we look at the questions, it stems from two big positions. One position is, well, we've looked at this for 100 years. No one's found anything. This doesn't make sense, Steve. So I know you just walked me through that, but that just doesn't make sense to me. And why wouldn't we have found that earlier? And more importantly, if you really did find a mistake, why does the theory seem to work and align with the experiments? So that lists some questions that we need to answer here. And as we go through our talk today, we're going to answer all 4 of those questions. So first, let's look at Einstein's derivation in a little bit more detail and convince ourselves that it looks right. So, and many of us have gone through the derivation. We know it looks right. So here's his tau equation. It comes down. Next thing he does a substitution. So we follow this blue line and we get this equation. If you follow those 2 steps as I've just outlined them, you will arrive at this equation. How about the next one? We pick up xi, this brown line. We come down here. We do the substitution. That comes down here. You get this equation here for xi. That is absolutely true. If you follow these 2 the blue line and the brown line, you will come up exactly with Einstein's equations as he is shown here. And you will be convinced that there's not a mistake here. And the mistake is actually hard to see because it's a mistake of omission. It's actually on this page, but we're going to build up to where the omission occurs and how it occurs. And in order to do that, I will have to introduce you to modern mechanics. So modern mechanics is my theory of motion, and fortunately, we can explain it relatively easily. In fact, we're doing so on one page. And the way we explain it is through 2 statements and 5 questions. Now, on this page, we have the statements and the questions separated, but since we're talking live, I'm going to intersperse them. So let's begin with the first statement. Imagine a street. On the street is a bus. On the street, standing next to the bus, is a jogger. So I'm going to ask 2 questions. First question is, how many nouns or things did I introduce in the first statement? Well, I kind of gave it away for you because I've underlined the 3 things that I've introduced: the street, the bus, and the jogger. And the second question is, based on your own knowledge and experience, can a bus go faster than a jogger? Well, while I've seen some fast joggers, I've also seen some buses driving on the freeway at 60 or 70 or even perhaps 80 miles per hour. So yes, I would say a bus can definitely go faster than a jogger. Let's move on to statement 2. A jogger is asked to perform one activity alone in this model, and that is to run at a constant velocity from the rear bumper. Remember, the jogger's on the street, so he's running from the rear bumper of the bus to the front bumper, turns around, and then returns to the vehicle's rear bumper. So now let's ask 3 more questions. So in that statement that I just read, if I were to give you the total length run by a jogger, can 1/2 of that length be determined? So let me ask that another way. If I was to give you the number 100, can we figure out what half of 100 is? Of course we can. It's 50. If I said that the total length was 80, of course we can figure out what 1/2 of that is. It's 40. Of course, I'm dropping units, which technically should be there. But nonetheless, it's a simple operation for us to figure out what 1/2 of a total is. So in that last question, did I ask for 1/2 of the total length run by the street, by the bus, or by a jogger? In our case, the first 2 don't make sense, and the only thing that was mentioned in that last question was the jogger, so that would be the answer. And the 5th point is, does the total length run by the jogger indicate the position of the front of the bus? Now, this is an important question because we're going to come back to this concept later, but think about this for a moment. If the jogger runs 1/2 of length to get 1/2 of L to get to the front of the bus, and then he runs another 1/2 of L to get to the rear of the bus, is he now at position L if you were to mark it on a coordinate system? No, he's not, because he turned around. He's at the back of the bus, so he's still at 0, even though he's run length L. This is important to show that our total length does not necessarily translate into the position of the bus. So there's a distinction we're making between the jogger and the bus. This distinction is pretty important. In fact, now that we've introduced the key concepts for modern mechanics, let's just use some of the vocabulary for modern mechanics. Modern mechanics is a 3-system modern model of motion. Relativity is 2. Modern mechanics consists of a stationary system, which was the street, a moving system, which was the bus, and an oscillating system, which is the jogger. Now, one could argue, well, the jogger is moving as well. Isn't that another moving system? And technically that is correct. However, if I have 2 things and I call them both moving systems, it gets a little confusing. So instead, this one we describe by its behavior, the cyclical nature of its motion. So we refer to it as the oscillating system. But notice we come back down on the bottom here to the key question. And that is, what is the length traveled by the oscillating system? So we're not talking about the length of the bus. We're not talking about the position of the bus. We're not talking about the position of the jogger. We're asking a specific question. What is the length traveled by the oscillating system? And if we know that length, we can ask a different question, which is, what is half that length? Now, I'm going to just ask a question that I'm going to ask you to file for future reference. That is, if I gave you a number, 50, and I ask you to take half of it, 25, what does that have to do with relativity? Okay, many of you are probably thinking nothing. We're going to come back and we're going to answer that in a little bit. So let's just plant that one, file that one away for a moment and continue on. So we're going to look at the key question. And our key question here is associated with the jogger's behavior of running from the rear bumper to the front bumper and coming back to the rear bumper. And our question is, if we're given that total length L, what is half that length? We're going to represent half the length by xi, our Greek letter that we've added to our alphabet here, and L represents our length. So mathematically, you can see xi equals 1/2 L. That's the fundamental equation that we're going to be working with today. So for all the rest of the math, we're either going to be talking about what is this length, 1/2 of the distance run by the jogger, or we're going to be talking about how much time it takes to run this length. So our goal is to simply come up with this equation, E equals 1/2 L, and we're going to express it in terms of the variables that we're given. And the variables that were given, I mentioned before, x, y, z, t, and v. So let's take a look. This is going to look like a lot of math, but we're going to go through it relatively quickly. So in statement 1, we basically say, well, we in our sentence, we said the jogger had to run from the rear to the front. That's one length. We're going to call that t. And then from the front back to the rear. That's another length. We're going to call that s. So t plus s is going to be our total length. Through substitution, we get this new equation. Okay, fantastic. Now we can say something else. We can say, well, we know that the jogger runs, the jogger we're going to name Charlie. And Charlie, we're going to represent Charlie's velocity with the letter c. And it takes Charlie some amount of time to run to the front of the bus, which is this lowercase t. We know that if we have time times the velocity, we get our length. So we can replace capital T with CT. Similar, when Charlie's running from the front bumper to the rear bumper, we can make a similar substitution, which we do here. Now notice I've written it in a specific way. We have a length, remember, xi is always a length, equals c, which is Charlie's velocity. This is time. There's time. This is 1/2 of that. So we're going to take this time part and pull it out by ourselves, which allows us to express the equation in this way. Xi equals velocity times time. Now let's work with this velocity equation because we have the time in one direction. If the length of the bus is x prime, then Charlie, and the bus is moving at velocity v, because it actually is moving away from us, then this expresses the equation that helps us calculate that amount of time. And there's a similar equation. There's a typo here, which I should have caught last night. This should be a plus. So this is s equals x prime c plus v, and I will correct that before I upload the files. And we will then replace both of those in this equation. So it's just simple replacement. Then we do some simplification. And because we set up here xi equals c times tau, we do that multiplication by c, and we get our final result. So here we found xi, which is 1/2 the length. We just have it expressed differently, and we know what the time is. It's going to be this value before you multiplied it by c, or this value time divided by c, and you get time. So tau represents the amount of time to travel 1/2 the length, and xi is the 1/2 the length. So that's pretty straightforward. Now, let's continue on because I want to show you another way of solving this. In my book, I refer to it as the subtraction mean equation, but there's actually a technically correct name for it, and it's called the incremental mean. The incremental mean is actually used quite heavily in artificial intelligence, especially in some forms of reinforcement learning. It also appears in statistics, and it probably appears in other places. So there are a lot of books that you can go to see the derivation of the incremental mean. I'm just going to show you what that derivation looks like. And what we're going to do is because this is a mean, basically, 2 numbers divided by 2 is a mean or an average, same here. We're just going to play with this one and use the incremental mean equation. So let's look at what that looks like. The incremental mean equation, notice that I could say 2 halves make a whole. So if I have half a t and I add another half of t, I get t. But that allows us to say 1/2 of t is you take the full t and you take half of it away, and you still have half a t. So we do that substitution, and we put that in here where we had 1/2 of t before. I do a little bit of rewriting. This is the incremental mean equation. So I won't go into what that is, but again, you can go and research that. Now we solve the incremental mean equation, and we do that in 2 steps because I want to show you a couple of important things. First, we're going to solve for the 1/2 t minus s part. So we're only going to focus on that. And so you take the t and the s from this side, you plug that in here, you solve, and you get this term right here. We haven't replaced this yet, so because I want to be explicit and show you this. Now, let's do the second step, is to replace the t part, which we also know from over here. So we'll plug that in, we simplify, it simplifies to the same equation, and we get the exact same result. So it's great. It doesn't matter if you solve it the normal way that most people are familiar with, which is take 2 numbers, add them together, and divide by 2, or if you solve it using this technique called an incremental mean. You still get the same answers. However, the way you got there is different. And if you're not familiar with the incremental mean, you might not recognize when it's being used. But now you will, because Einstein uses the incremental mean in deriving his equation. So it gives you some additional insights to Einstein's derivation. Now, the way he does it, he actually, to get to this point, he does another complicated step, which is a partial differential equation. Let me go back 1 slide. But if you look at his derivation, he starts with this equation, he starts with this equation. You can solve it by just taking those 2 things, dividing by 2, and multiplying by c, you will get this result. So there's an easy way for you to check Einstein's work and the work that we're walking through today. So notice a couple of things. Here's our step 1, which appears here. It also gives meaning to what this term means. A lot of people will say, if you ask what this is, they say, oh, well, that's the adjustment to time without the additional context. You now know exactly what it is. It is this term from the incremental mean. And you see this term, which is properly solved. Now, I claim that this is the correct term because of this replacement, and this is where this is the source of Einstein's mistake that leads to the 1 = 0 problem. So which is stated here, and it's really, now that you know what's going on, you can see it's a statement of omission, but it's hard to detect as a statement of omission if you don't know what was omitted. That's why we went through the process that we just went through. So remember, there were 2 steps in solving the incremental mean. Step 1 was you solved this part, the 1/2 t minus s. Einstein does that. And when but then there's a second step, which is to replace t in that equation, which Einstein does here. So he does step 2 when he solves for xi, and then xi comes down, he does his final substitution. That's why this numerator is in fact correct. Now, when he does his tau equation itself, he just comes across, he does not perform step 2, does his substitution, simplifies. This is an incorrect simplification, and because of that, that is why we get this the inequality. And if you pick the right values, that's why you get the inequality that says 1 = 0. So it's a statement of omission, and this is pretty powerful because if you're going to make the statement Einstein says 1 = 0, which is mathematically incorrect and it invalidates the theory, the next question that might be asked is, well, where does he make the mistake? And now we are able to show where that mistake is in fact introduced. So the next question, however, that naturally follows is, well, his theories seem to work. And I know when I've tried to show anomalies and problems in Einstein's derivations elsewhere, people like to jump to their favorite derivation. So you start with Einstein's 1905 paper, and the person you're talking to says, well, that's not true because in this other derivation, he doesn't say that, and this other derivation is right. So the nice thing about the 1 = 0 find is that it occurs in at least 3 of Einstein's derivations that I've looked at. So it may look a little different. Here he uses Greek letters. Sometimes he uses letters with primes on them. Sometimes he squares them. Sometimes he takes the square root of them. The nice thing about 0 and 1 is if you square them or if you take the square root of them, they stay the same. So it doesn't matter. So if you see any of these equations and in sort of any of these forms, they're all forms of Einstein saying 1 equals 0. And when he does that in his derivation, that's where he introduces the mathematical mistake, because at the end, or it's a way for us to determine that there is a mathematical mistake, because at the end we can evaluate it with x equals 1, v equals 0, t equals 0, and you will end up with Einstein's statement saying 1 equals 0. So I said that we needed to express these terms in terms of things that we will actually give, which is x, t, v, and c. And if you look at the equations we ended with, we have an x prime here, which represented the length of the bus, and an x prime here that represented the length of the bus. So we need to get rid of that. How do we do that? Well, we know some facts from classical mechanics, which is if the bus had at time 0, the rear of the bus was at position 0. The front of the bus is at position x. Not only is that a position, or excuse me, x prime, not only is that a position, it's also the length of the bus because the rear of the bus was at position 0. Well, at time t in the future, the bus has been moving for some amount of time. It's now at position x. Okay, fantastic. And that's represented by this classical mechanics equations. We started, the front of the bus was here. We move forward at some velocity for some amount of time. We now have this new position. Well, this was also the length of the bus. So I'm able to move this VT on the other side and do replacement substitution, which is what I do here and here. So we're able to express our equations in the form that we were asked to, which is fantastic. But notice something, the equations that I came up with here are not the same as Einstein's equations. And in particular, Einstein has this beta term that will come into play in his, and they don't exist over here at all. So we'll need to talk about that, because that should raise some questions as well about how can you have such radically different equations and have them perform equal to or better than Einstein's equations. We'll get to that in just a moment. But before we get there, I want to fill in our table a little bit more with some insights. And before I do, I want to go back to one slide, because there's something else I want to say here, which is if you go above the text here before this statement, you'll see how Einstein puts together his pieces. And when he puts together his pieces, he tells a story. And that story is he has a moving system, he has a stationary system, and he has a ray of light. That ray of light is the oscillating system. He actually uses a third system in his derivation, but he doesn't recognize it. And because he doesn't recognize he has a third system, he mistreats his 3-system derivation as a 2-system derivation. What does that mean? Well, there's some huge implications for that. So remember, he only has 2 systems, a moving system and a stationary system. Well, associating any equations with a stationary system doesn't make sense. But we have this length equation, which we know is associated with how far the jogger has gone, or in his case, how far the halfway for the ray of light to have traveled. He doesn't have that in his final thing. So he has to associate this equation with the only thing he does have, which is the moving system. That association of this value with the moving system, which already has a length, he gives a name. That's called length contraction. The other thing that has to happen is he has to adjust these equations, because again, for us, they represent things associated with the jogger. He doesn't have a jogger, or in his case, it would be his ray of light. Since he doesn't explicitly recognize that, he has to associate them with the only thing he does recognize, which is the moving system. And in doing so, he introduces the concept of time dilation. So you can see if you take a 3-system derivation, which is what Einstein does, and you mistreat it as a 2-system derivation, then you must explain some of those anomalies away. You must explain things that are associated with the oscillating system, but you don't have that. You're forced to explain it anyway, and he does it via terms called time dilation and length contraction. So that allows us to fill in this table a little bit more. Modern mechanics is a 3-system theory of motion. which we talked about: stationary system, moving system, oscillating system. Relativity is a three-system theory of motion. He uses a stationary moving system and also a ray of light, which is his third system, but he doesn't acknowledge it, so he mistreats it as a two-system theory. As we saw in the derivation, xi is a length, and a tau is simply the time to travel that length. So again, if you have a length of 100, what is 1/2 of that length? That gives you xi, that will be 50. And you saw that in theory, when I first asked that question at the beginning, you probably thought that has nothing to do with relativity, but now you can see it's simply Einstein is finding half, or an average. So let's continue on, because at this point, we're probably saying, well, while we've addressed the theoretical side and we've shown what's going on, and perhaps, okay, that makes sense, Steve, I can see what you're saying, and you've shown me that it exists in other places, but his theory, it's still experimentally supported. So I'm not completely bought into what you're saying yet. And in some cases, his theory is the only thing that explains certain things. There's no other theory that explains those other things. So how are you going to address that? Well, let's take a look at it. Let's first acknowledge the elephant in the room, which is we have different equations. So how are different equations going to give us the same answers? And do they always give us the same answers? That's interesting, because the equations are not equivalent. So let's take a look. And what we're going to look at is Einstein's famous energy equation, E equals mc squared. This is another one of Einstein's papers that was published in 1905 called Does the Inertia of a Body Depend Upon Its Energy Content? And in that paper, he walks through a derivation. I'm going to take away all the words from the derivation, and we're just going to walk through it so that we can see how Einstein arrives at this equation. He begins with his equation. Now, this is the equation that we had on the prior page. It's just rewritten in a different form. I've brought the beta term in, and I've kept x prime. That's in effect what Einstein does. You replace x prime with L, because that's what he does in his paper, and we get a difference equation. So L is the original, and L over the radical thing there is the adjusted value. It will be a larger value than the original one, so we're looking at a positive difference. So you can think of this as stretching a rubber band. The rubber band has a certain length, and if you stretch it for a new length, then you can say, well, what's the difference in length? That's all this equation is saying. However, in 1905, solving this type of equation without the benefit of a calculator or a slide rule or a computer is pretty hard, because we have that square root in the denominator, and solving for a square root by hand is not necessarily the easiest thing to do. Fortunately, mathematics comes to the rescue, and there's a technique called a series that helps us. It's a tool, a common mathematical tool that allows us to transform this equation into something that we can solve that isn't going to require pulling out all of our hair. So we do that, and we convert it to a series. Now, technically, this series where we have this little equal sign, that should be an approximate sign, because the series is an infinite series, and we're only going to use so many elements of so many expressions of this series. But that's minor at this point. We're not going to worry about that yet. But Einstein does say in his paper, you know what, of this series, we don't need to worry about any term that has v to the fourth or higher. It's pretty small, it's immaterial, ignore it. So he ignores that part and will only keep this first term. So, and he says this in his paper, he says, neglecting magnitudes of the fourth or higher orders. So he says, ignore all that stuff that's on to the left, only worry about this term. So we only use that term. Then you set this side to the kinetic energy equation, 1/2 mv squared, solve. Then for nomenclature, because E is the way that we write it today, we don't use L, you end up with E equals mc squared. There's a lot of other derivations out there. Many of those derivations are not completely correct because they ignore things or they introduce kind of convoluted ideas. I think Einstein's derivation, you can see it right here, it's actually quite straightforward. You have the original, you find a difference, that's hard to solve, you convert it to a series, you truncate the series because that's what he says to do, you replace, you assign this with kinetic energy equation, and then you solve, you simplify, and you end up with E equals mc squared. So this allows, this slide tells us two things. One, how Einstein arrived at E equals mc squared, but it also shows us that any experiment that aligns with E equals mc squared can be traced back to relativity. You can say the experiment supports relativity. That's a true statement. The question is it the only theory it supports? Let's take a look. So let's look at the modern mechanics equation. So we saw, and modern mechanics is derived from classical mechanics, which is why I say classical mechanics based equation. But it's modern mechanics, and we have the equation. We do the same thing. We do the difference. But remember, for us, we were using 1/2 of L. So we're going to use that instead of x prime. So we have our difference equation, and we could solve this. There's no radical in this equation. But for symmetry, we're going to convert that to a series. And we do. Now notice, they're not the same series. Right over here, you can see I have a different constant for the second expression. I have 1/2. Here was 3/8, and each of, if you look at the rest of these terms and they're expanded, they're not the same, except in the first term, which Einstein says ignore everything except the first term, which means it also leads to this. Replaced by kinetic energy, simplify, do the final replacement of E for L, leads to E equals mc squared. Now this is important for two reasons, this particular slide. One, it shows that E equals mc squared is not unique to relativity. I know I've heard people say, nope, you need the radical in here. That's the only way you can get to E equals mc squared. No, it's not true. You just need to convert it to a series and make sure that the series has the first term. Make sure you have something that goes to the fourth in order. So if you had, they get truncated because Einstein says to truncate them. But it also shows an important other feature, which is that truncation, when we truncated it and we got rid of it and we made it simple, at this point, this really needs to be an approximate symbol. Because this, if it's any statement of equality and it's hard equality, then you can work mathematical equations forward or backwards, which means we have to be able to work this equation backwards or backwards to one of these. And you can't, because these two are not equivalent, this cannot work backwards equally to both of them. And the reason they can't is because of this truncation. So this is better stated as E is approximately mc squared. And it's true, it's truncated. So you can see that even if we didn't walk through the modern mechanics derivation. But it does show in another important fact, which is modern mechanics also produces E equals mc squared. And the power of this is every single experiment that has been conducted on E equals mc squared and has been used to support relativity theory by this derivation also supports modern mechanics. So right off the bat, we show strong experimental support, even though we started with different equations. So that allows us to build our table a little bit more on the left-hand side, on the right-hand side here. So both produce E equals mc squared. That's a little sloppy because we have that truncation. It really should be E is approximately mc squared. We saw why on the last slide. And as I mentioned, every experiment that validates this equation also validates modern mechanics. So that raises a question. Okay, Steve, great. So you've shown that you have an alternative that works equivalent to relativity. Why should I care? What I really need is something that's different. I want you to make a different prediction than relativity. Can you do that? Well, let's take a look. And for this, we're going to look at the Michelson-Morley experiment, which is widely accepted as one of the key foundational experiments associated with relativity. Now, I'm going to just call out on the left-hand side just a little bit of their text from their experiment, where they set up what they are expecting to see. And they say, in one path, we expect to see something that behaves according to this equation. On the other path, we expect to see something that aligns with the second equation. And in terms of differences, we're expecting that to be governed by this equation. Okay, fantastic. So we know what equations they're working with. And we also know what D is because they tell us we're working with yellow light, and yellow light has a specific frequency, which we have here. So let's just do the math. So we put D into their equation and we get a new number. It's simple, it's just math. And we're going to do the easy case when velocity is 0. So we're not worried about any shifts. We're expecting 0 to be the difference that we observe. So, and we do the math here, D, we get this, and the difference is in fact 0. Yay, success, victory, it seems to work. However, notice the frequencies that they expect for after the light has returned in their device. And their experiment is based on sending light, bouncing it off some mirrors, observing the light, and then measuring the size of the cycle. So it's one that depends on the human eye being able to see the light. Well, the human eye has a range of frequencies that we see, we translate into colors. And that range goes from 4.3 all the way to 7.7. This is 10.4. This is outside of the range of the human eye to detect. So this is a problem because it says we can't see the ray of light that they were expecting to see. So yes, this part is right, but this part seems wrong. And the other thing we note is that their experiment does not count cycles, right? It's an experiment in hertz, which is cycles per second. But they don't have a frequency counter or any of that type of technology to actually physically count how many cycles have occurred. So, their experiment's not capable of counting cycles. And based on this, their intermediate results are things that you should not be able to detect with the human eye. So let's look at modern mechanics. Now, modern mechanics, again, you look at their equations, you recall these from our earlier slide. He uses capital V in their derivation. This was 1887. Our modern convention is to use C instead of capital V. And D, in our case, was the length of the bus. We did have cyclical motion, which is why we're able to work here. But in our case, remember, we average. They sum. So that's the difference. If you're looking at how relativity is interpreting those equations in how Michelson-Morley originally analyzed it, they added, we average, we sum. And so when we use the adjusted equations, again with V equals 0, we still get a difference of 0, yay. But now the light that we expect to see as intermediate waves are exact yellow light, so there's no difference, which was what we would expect when velocity is 0. So this is consistent. It falls within the range of the human eye, and because of that, and it's a frequency-based experiment, we can detect it and measure the wavelength using their device called an interferometer. We have consistency. Okay, so how do the two approaches stack up in evaluating Michelson-Morley? Well, let's look at relativity first. The Michelson-Morley experiment expected to be able to detect an Earth orbital velocity of approximately 30 kilometers per second. That's how fast we're orbiting around the sun. If you want to accept the relativity approach, you have to reject that hypothesis. They will not accept it. They accept that you can't detect the Earth orbital velocity, so they say, nope, you need to replace that with 0. Then we say, how about the actual results? We measured some actual results, and in their paper, Michelson and Morley say it's probably 1/6, certainly less than 1/8. Mathematically, that's about 5 to 7.5, 5 to 8 kilometers per second. Okay, they say, nope, you have to throw that out. That's experimental error. Reject those measurements. Okay, so down here we say, well, how big is the error? Though the error should be 5 to 8 kilometers per second, unless you decide you're going to ignore everything about the experiment. We're going to ignore the hypothesis. We're going to ignore the results. Then you can say the error is 0. And of course, we've already talked about it not being aligned. How about modern mechanics? We accept their hypothesis. They said 30. We're going to keep their 30. We accept their results, and their results are the measurements. Remember, there's an equation that's used to convert the results into a velocity. We're using a different equation, but we're keeping their results. We accept them fully. And our observed error is smaller So it's either smaller or we accept everything. And as you can see, they reject everything. And ours is frequency-based, and that aligns with the device. Now, this is an important statement. And it's one that I think is really critical, which is if you want to accept a relativistic interpretation of the Michelson-Morley experiment, you have to reject their hypothesis. You have to reject their observed measurements. And if you've rejected what they expect, and if you reject what they actually observed, you've in effect rejected the whole experiment. So I don't understand how one can claim that this rejected experiment is support for their work. And that takes us to these last two of three that we need to look at. So one is that modern mechanics looks at evaluates at 30 kilometers, and it does so with less error. And in order to do relativity theory, you have to reject their hypothesis. You have to reject their actual results. Basically, you have to reject the experiment, but still claim that it supports you. Now, there is another experiment out there, which is Miller repeated the experiment in 1933. And in 1933, I think his experiment, when you analyze it using the original approach, came up to about, I think it's 11 kilometers per second. So bigger, but farther from zero. So a lot of people look at Miller's paper and say, nope, he must have made way too many mistakes. There's something wrong with it. We're just going to dismiss it. It's completely wrong. So you don't get experimental convergence. So instead of digging deeper, you just say, we're going to reject it. We don't reject it. We look at it. When you evaluate his data, which is also contained in his paper, and you use the revised modern mechanics equations, his experiment also detected 30 kilometers per second. So you have experimental confirmation, two experiments designed to measure the same hypothesis, and they got the same result. We have experimental confirmation with less error. So in this case, we can objectively say that modern mechanics makes a different prediction, and it makes that prediction and the difference between its expected result and the actual result has less error than the expected result and actual result that relativity does. So objectively, quantitatively, we can say modern mechanics performs better. Now, there was an objection that a proof that you'll find on my website in my book, and it's the spherical wave proof. I still love this proof, but I don't lead with it anymore because the proof isn't in all of his derivations. So I like the 1 = 0 approach that we've shown earlier. But this is important because Einstein says, you know, I've done all this work. For me to check my work, I need a proof. I need to say that everything sticks together. I don't just get to create an equation and say, look, it's done. So he says, I'm going to do a proof that says if I start with a spherical shape and I run them through my transformation equations, my transform shape is spherical. And he says that right here. He says the transform shape is spherical in the transform system. Here's the transform system values. And he says this is spherical. Well, to have a sphere, you need two things. You need to adhere to this equation. That is part one. Remember, we have a couple of omissions here, and they're not intentional omissions. They're just omissions. In this case, the omission is a sphere requires that all points be the same distance from a common center, which means we need to check this term and make sure it is not changing. Well, an easy way to test that visually is just draw the shape. So take a unit circle, a unit sphere, pick a large enough velocity so that you can see what's going on, plot it on a piece of paper. You can draw it yourself. If you do that, you will find that it is not a sphere. You can look at it mathematically as well. It's up to you. So, and the reason is, again, a statement of omission. In order to do this, you need to check that this is constant and unchanging. Einstein did not perform that check. But if we do it, we show that it fails. So just additional confirmation that there is a mistake, the one that we've outlined, and we know the source of that mistake. It's because he used the incremental mean. He did not take step 2 of the incremental mean. Probably the other big part is he took a 3-system theory of motion that in his case consisted of a moving system, a stationary system, a ray of light, and did not recognize the role that the ray of light plays, and that the equations are describing the behavior associated with the ray of light, not with the moving system. And that brings us to our top 10 insights that disrupt modern physics. So let's see how we did. There were a couple of questions that we said we wanted to go through today. The top two were on the derivation. The bottom two were on the experiments. So there's a large body of work that appears to support Einstein. Yes, in some cases, because it's an approximation. But in other cases, it doesn't work because it requires either ignoring parts of the experiment and us kind of finagling it. But I think Michelson-Morley is a great case of where it doesn't work, and E equals mc squared using approximation, showing that there's multiple ways to get somewhere, is an example of where it works. Now, some people still might not be comfortable with approximation, but I know when I was younger and probably in primary school, somewhere, and you learn how you're learning trigonometry and you don't know all the numbers and you don't know what pi is, and someone says, just use 22 divided by 7. And so you do that, you get 3.14 and some numbers. That's fine while you're learning. But if you look at enough digits, at some point it becomes wrong. It's no longer the same. And that's essentially what's happening here with that truncation we walked through earlier. It's going to start off right, but if you get far enough into it, eventually it's going to be incorrect. So how do we do on our goals? Let's see. We had an easy to remember phrase that clearly states what the mistake is that invalidates Einstein's theory of relativity. And that phrase is, Einstein says 1 equals 0, which is mathematically incorrect, and that invalidates his theory. About number 2, how can these insights go undetected for 100 years? Well, as we've walked through, when there's a statement of omission, if you don't know what was omitted, you don't know it's not there. Of course, if you don't know something's not there, it's very, very hard to catch. But now that you know it's there, and we've walked through the equations in 2 different ways, so it gives us a way of checking our work, you can now see exactly where and how the problem was detected or introduced, and how it went undetected for so long. Because many of us, myself included, have looked at Einstein's work for years or decades, and it's hard to see if you don't know what you're looking for. How can a theory be incorrect and still provide useful answers? Well, we've shown that it can, because it's a similar approximation in many cases. They come up with similar values. And the trick is to find that class of experiments where they make separate predictions, radically different predictions. And we use Michelson-Morley as that experiment. And the nice thing about Michelson-Morley is the difference between the predicted value and the actual value is smaller for the modern mechanics side than for the relativity side. So therefore, we can say that the modern mechanics equations and predictions perform better. And of course, we've introduced modern mechanics. So if you can remember the example between a bus, a street, and a jogger, then you can understand modern mechanics. And all you have to do is remember that main equation, which is you're trying to find half the length that the jogger has run. That's the core math equation. Yes, we made it, we expressed it in different terms, but ultimately we're asking questions about the jogger. So just to summarize here, here's our top 10 insights that disrupt modern physics. And I think at this point, I just want to acknowledge a few people. I want to say thanks to my daughter, who did some illustration in Disruptive. So I'll thank her for that. And Grant Dexter, who I mentioned earlier, for being a strong partner in helping me edit the book. It wouldn't be the work that it is today without their help, as well as countless friends, colleagues, and relatives who played roles throughout there. There's too many to mention, but a ton. And people who like to ask and answer questions. I think that's really important too. There are some links if you're interested in this talk. I think it will be on David's site later, and you can certainly go there, but I do have a paper that is out there. It's a preprint. I'm still trying to find a journal for it. And then, of course, my website is out there as well. So I think at this point, that wraps up our talk today. It did take a few minutes longer than 30 minutes. So thank you for entertaining me and going a few minutes extra. And with that said, David, I'll hand it back over to you and take your lead from here. And I can't hear you if you're talking.
Thank you so much. It even has my name with a mute right next to it. I can just blabber on. So, thank you so much. It's great. I really enjoyed this presentation. I've seen numbers presentation by you, and each time it gets clearer and clearer. But I have a bunch of questions. But before I do that, I do want to say if you have questions for our guests or comments, I will put this down there. In the chat, you want to put question colon or comment colon. I know I've seen some go away, but there's been a ton of chat there. So please put your questions in there. Also, we do have people in the green room, of course. So those people will be able to come up later. I usually do that later on. But I have questions myself. A lot of them. Okay. First question is interesting because I know Dr. Karazani was my mentor, right? And he showed special relativity wrong in a different way. Now, the two V's that I see in your equation, that are those two different velocities?
In my equations, there should
Yes.
be
Okay,
one V. Let's see. In
Right.
my equations, there should be one V, which is the velocity of the moving system. In Einstein's original paper, if you go back to his German version, or if you look at the Michelson-Morley paper, they use capital V to represent what we now call C, the speed of light, and lowercase v to represent the velocity of the moving system. I think having a capital V and a lowercase v is confusing, so I'm glad that the scientists of past decided to change one to be a C and use the other one for V. In my derivation, there is a difference between another difference between modern mechanics and relativity is that C, in our case, the velocity of Charlie that's the velocity of the jogger of the oscillating system. In Einstein's theory, that velocity is the speed of light, and he fixes that at C, which is the speed of light through a vacuum. So in this case, modern mechanics is also more generalizable across other phenomena, not just light.
Yeah, and the other thing is, though, in Einstein, he has a V and a V prime, doesn't he?
I don't know if in some derivations in other books I've seen V and V prime. I've seen U.
That's besides C. That's besides
in other derivations. Yes.
Right. Okay, gotcha. Okay, we do have questions coming up. Let me ask you a few of mine here. One frame for the two moving objects. Is that correct?
So you have, just think of it like you would just going out to your street. You have a street. You have a bus, which is one moving system. That's the bus. And you have the jogger. So any noun that we create in our environment becomes a system. So our stationary system, the street, it's a reference system of which we compare our motion of the bus against. And it's also, when we're measuring motion, it's how we can compare the distance that the jogger runs. The only difference here is that we're asking the jogger to do something. We're saying, jogger, run to the front bumper and then turn around and run to the back bumper. Now notice what that means. There's an implication in there that I didn't say, because I asked a question earlier. I said, can the bus go faster than the jogger? And we said, yeah. So the important implication here is, if we're going to ask this jogger to do what we've asked him to do, which is to run to the front of the bus, the only way he can get to the front of the bus is if the front of the bus does not meet or exceed the velocity of the jogger. So in Einstein's world, what does that mean? It means if he's going to force oscillations to occur, the only way he can do that is by limiting the velocity of the moving system to be less than c. So Einstein's theory creates a constraint that says nothing can go faster than c. Ours doesn't say that. Ours just says, if you go faster than the speed of the jogger, if you go faster than c, these equations don't apply. They just don't apply.
Okay. Let's put some questions now from people. I don't know if you can see that, Mr. Bryant. If the spherical wave proof had passed, would relativity theory be correct? If yes, why? Is that something you're familiar with?
So if we go to the spherical wave proof, which is somewhere back in here, the problem with it is that it does in fact fail. So if it had passed, then it could be evidence that it sort of makes sense. And in fact, there's a strong argument here that if you think of it this way, if you think of Einstein's paper as consisting of 3 stages: pre-proof, proof, post-proof. Anyone who argues Einstein's work after the proof, and they say Einstein's wrong, and they say because of this paradox or because of that, at that point, the game's already up, because A, the proof exists, so people can point to the proof and say, this is why it's right. And people can say, they can use any relativistic term at that point in time to counterattack, which means they can even say, you don't understand relativity, and just simply dismiss you with sleight of hand after that. If you go to the other end and you only show the mistake that I showed, 1 equals 0, then someone could argue, well, Steve, 1 equals 0, you might be saying that, but it must be insignificant because the spherical wave proof passes. But when you look at the spherical wave proof, it doesn't. And so, it is a critical component because it does give evidence that there is a math error. If the spherical wave proof actually passed, it would be harder to basically defend the stance that there is a significant mistake that occurs earlier in Einstein's work.
Okay. We got another question here. I think I have the answer and I can put up there, but it is, where's your main repository, website, URL, where your works are? Can they go to Stephen B. Bryant? Is that a good place?
Yeah, if you go to stephenbbryant.com, I think I link a lot of stuff there. My old site is still active, relativitychallenge.com, so there's some stuff there. I'm now trying to make, I think, David, some of the material might be on your repository as well, or links to. I'm trying to put some of the work on the preprint server, and as we saw earlier, one's on the preprint server. I think it's pronounced Vixra, xibra.org. And so I have a paper up there too. Okay.
But you can go to stephenbryant.com, and even if you have questions, you can always feel free to, I'm sure, to contact you, correct?
Yep, it's out there.
Okay. So another question, motion of what? When it's not joggers and buses, what is the what that is in motion?
So whenever we talk about motion, we do have what, and it becomes a noun in our series of things. So basically, think of nothing, and then you create things. And if we were talking in computers, we would talk about instantiating an object, for example, in an object-oriented programming paradigm. In this case, we're instantiating systems. So the first system we create becomes our reference system, and it's the system on which that we plot other things. If you're writing graphic software, this might become your world. Then on top of that, you place other objects. If you're writing a simulation software package, those objects could be airplanes, they could be buses, they could be people, whatever they happen to be. In our case, we have 2 objects that we've instantiated, or 2 systems. One is a bus, so we place that on top of our street system, and the other one's a jogger, and we also place that on top of our street system. And our street system, if we wanted it to move around as well, we need to plop it on something. Maybe we plop it on a planet, and so now there's all sorts of things that we can do. But for now, I think that complicates things. Just keep it with a bus and a jogger and a street. And again, those are the concrete examples, which their abstract names would be the stationary system, the moving system, and the oscillating system.
Okay, I have another question. Why doesn't it apply to the equation when it's faster than c?
So for that, if we think about, again, the velocity of the jogger is c, and we've asked the jogger to go to because the jogger's name is Charlie, so we're just using C for Charlie. So we say that Charlie must go to the front bumper and turn around and go to the back bumper. If the bus is going at 60 miles an hour and Charlie can only run at best, I don't know, if it's me, let's say 2 miles an hour. I don't know how fast I can run, 3-4 miles an hour. If the bus is going faster than me, I will never get to the front of the bus. It doesn't mean I've limited the bus's velocity. It just means I cannot have Charlie do what I've asked Charlie to do. So this is really an important distinction here. These equations apply to Charlie. So if there's a limitation that occurs, it's on the the jogger, or in our case, to use the abstract terms, it's on our oscillating system. So it does not impose a new constraint on the moving system. It does not impose a velocity limit on the moving system. It only says, if we want Charlie to be able to do that cyclical motion that we've asked Charlie to do, then in that case, the front of the bus has to be reachable by Charlie, and which means the bus has to be traveling at a slower velocity than Charlie. Otherwise, Charlie will never get there.
Okay, I'm going to put some other things that are sort of comments. Here's one. I believe that SR and GR clock dilation is caused by the same thing, acceleration. What again, you talked about time dilation. Now, time dilation is this idea that there is time, and that time somehow can be, actually changed. What can you, I guess, maybe go over again what your work on and time dilation? Is that real? Is it not? Is it just, are we making something about something that's not really time changing?
Yeah, absolutely. So if you go back to the slide I have up now, David, I'll use that as an example. So in step 4, you'll notice Einstein gives us an equation here. And this equation has c squared over c squared minus v squared x to the prime. Well, you can move the c squared and just divide by 1 over c squared, and you will get 1 over 1 minus v squared c squared. So it looks close, there's no radical. Now, earlier in Einstein's paper, he says b squared, which is what you would have there. But here, he only shows it as b. So he's lost a term. Now, you could say, why does he lose a term? Because he doesn't explicitly say he's lost a term, but he does lose a term. He loses a beta term. So how does that happen? And the reason is embedded in this equation. And it goes back to what we talked about earlier, which is, and it's not up here, but if you look at Einstein's equations, when he does this transformation for the y-axis and the z-axis, there's actually a radical in the denominator. Okay. Einstein has a two-system theory of motion. He does not have an oscillating system. He has some equations. These equations have to be associated with something. They can't be associated with the street. That's nonsensical. So they have to be associated with the moving system. Well, we have equations that are associated with the moving system. Those are the Newtonian equations. So if you want Einstein's equations to be associated with the moving system, they're going to be replacements for the Newtonian equations. Well, in order to do a replacement, you have to get rid of that radical for the y and z transformations, because they have to be untransformed. And that's why he loses a beta term between here and a statement of these equations earlier in his paper, where you'll actually see beta squared, beta, and beta. But that drop he doesn't explicitly talk about. It's implied because he's using that as a replacement for the translations equations. And once you lose that beta term, this term right here, that becomes the source of time dilation, because that term adjusts his time equation.
Okay. All right. Let me bring that down here. And let's see, we have some more. It says, can we ask questions here? Of course. Let's see, put this up here. Would the assumption that the two-way speed of light is the same there and back have any implications for Michelson-Morley?
So let me see, what the assumption that two-way light is the assumption that two-way speed of light is the same there and okay, I see what we're going for. So this is actually interesting. So if we go back to all the derivations, I wish I didn't have the typo. So I'm actually going to go to the Michelson-Morley one. All the derivations will have an equation that looks something like this for what's going on, and what's happening in this bottom and the numerator, or excuse me, the denominator is the adjustment. So the jogger plays the role of the the speed of light. So let me try a different example, because it does, even though my theory doesn't have anything to do with relativity, it will explain an interesting concept. Imagine you're sitting on the bus and the bus isn't moving. And right now you see Charlie running backwards and forwards, just going backwards and forwards from the rear bumper to the front bumper, from the rear bumper to the front bumper. And you look at that and you look at your watch and you go, wow, Charlie's pretty fast. That takes 10 seconds. Well, maybe Charlie's pretty slow, I don't know. It takes 10 seconds to go from the front of the bus, or from the rear to the front to the back. It's 10 seconds. Fantastic. Okay, so that's 10 seconds, whatever. Then someone gets on the bus and they say, hey, I'm late for an interview. I don't even have a watch. And you say, here, take mine. So you give them your watch. Now the bus starts moving and you're trying to figure out something. You're trying to do your timing for a presentation that you're going to give, let's say, at 7 a.m. Pacific time. So you're trying to do your timing.
Oh, rub it in, will you?
And you don't have a watch anymore. How do you know your timing? Well, you knew earlier that Charlie, if that round trip was 10 seconds. So you're just going to use Charlie as your stopwatch. Okay, so each time you see Charlie go back to the back bumper, that's 10 seconds. Notice what happens when the bus starts to move. It takes Charlie longer to go to the front. Faster to go to the back, because the back is approaching Charlie as he's approaching Ed, but it takes longer to go to the front, and overall it's going to take Charlie longer. So I'm looking at Charlie and I'm seeing this oscillation and I'm thinking to myself, 10 seconds, yeah, okay, I have plenty of time, this presentation, wow. And if the bus is going fast enough, I get on the line with David and David says, how long's your presentation? And going, well, I was on this bus, we were on the freeway, a little bit of traffic, but it's 10 seconds. I saw Charlie, he only made it to the front of the bus and back once. Meanwhile, the person next to me in their car who is driving to their interview, who has my watch, they're going, that wasn't 10 seconds, right? So now you can see how when Einstein introduces the idea of a perspective, how that allows us to introduce concepts like time dilation, which is the example that I just illustrated. Now I use the x-axis, Einstein actually uses the z-axis, but conceptually it's the same idea.
But is time dilation what people normally talk about, just clock retardation? That is, time itself isn't slowing down. It's that how we measure it is changed. I mean,
That's
just
right.
like, so there's a difference between, one of the things I got the terminology from the MPA, the old MPA, us, is that they talked about clock retardation. The same thing that Ron Hatch used to talk about when he talked about the satellites. It wasn't that time was slowing down up there. It was that they're mechanical clocks. Even atomic clocks are mechanical because everything's made of atoms, and that when they got in orbit, there would be a time difference, and that time difference was not because of time, but because of the gravitational field, because the clocks don't, if you run in a high gravitational field and a low gravitational field, they're going to run differently. So that's what you're saying in the same sense, right?
Exactly.
You're not saying that what's happening is the person who is seeing time that they think they're 10 seconds because of Charlie or whoever's running there, for them, time is slowing down. But that's what the conclusion is for time dilation, right?
It's really what you said, David. It's kind of the clock mechanism is behaving different because of motion, but it's because it has to cover a longer distance as a result of that motion. And as a result of covering a total longer distance, we've changed the time equation. But that doesn't mean time is going slower. It means our mechanical device is we have to account for the motion. And you can correct for that, just as Ron Hatch mentioned in some of his GPS talks. You correct for that in GPS all the time.
Right. And the people jump up and down and say, see, time is slowing down. I think that's one of the things that, the fantasy of Dr. Karazani, who was the reason I got into all this, he always said that human beings love fantasy. They just love fantasy. It's much more much more fanciful to think that time itself slows down than to think, oh, it's just a clock and it gets affected by the physics around it, sort of like the unicosms, the microcosms, the macrocosms of Borchert's world. That's really what's happening, but it's not as romantic. But
That's right. And
okay.
what I've also found, David, is that part of our challenge in terms of getting the message out is we need crisp, clear messages that we can all share, right? And if you put your hand on a pane of glass and press hard, you probably won't be able to break that pane of glass. But if you get a sharp, pointy object and then you apply pressure, you can break through that pane of glass. So for us, we need kind of that core message, which regardless of whether you agree with everything I'm saying, if you believe something's wrong, you can add this to your tool chest. Einstein says 1 equals 0. I can show you why that invalidates it. I mean, it's a pretty easy argument, and people will say, well, no, he doesn't say it. And you're able to walk them exactly through why and where they do. This is important because I think there's a lot of folks out there who, let's just face it, I don't think people are out there to get anyone or be intentionally evil towards people. Well, most people aren't, at least. But there's a lot of folks out there who have a vested interest. They've been looking at this for years or decades. They haven't seen it. Their trusted friends haven't seen it. Their senior statesmen haven't seen it. And it's one of those things, well, there's this whole group of people who haven't seen it. Why should we believe you? And this is a case where you have to say, well, number one, there's a lot of other people who are saying the same message now, which is why I think it's important to add that message to your toolkit. And the other part is, this is something that you can test easily, right? Just like we did here. Just use these equations. Put x equals 1, v and t equals 0. Try it for yourself. It doesn't take a lot of time. What I find, though, is that people, because they have such a strong belief, they have the education, they have all their peers, they have other folks who are saying this is right, that sometimes they don't want to even entertain the idea that it might be wrong. And that's where science can get stuck, is everything should be fallible. My theory, my alternatives are fallible or potentially fallible, meaning, and by that I should not use words that I'm not sure of the meaning, but they can potentially all be proven wrong. And I think to some extent, even though people will say, yeah, Einstein's theory might be proven wrong, most people, when you look at them, they don't believe that at this point. And so they're not willing to even entertain the fact. In fact, my last paper that I submitted somewhere, they sent back a letter saying, no, you're not right for our journal. And the reasons they gave, indicated that they did not read my paper. One paper that was rejected, it said, Steve, we're rejecting your paper because you talk about gravity and that's covered elsewhere. And I wrote a letter back saying, I don't mention gravity once in my paper. And they said, well, that may be true, but we're rejecting you anyway. So it's one of those things where it's really hard because this disagrees with what people believe to be true. And once you get to someone's emotional convictions, their core, it creates a visceral reaction. So you can put this to the test. You can say, if a theory says 1 equals 0, is that theory wrong? And most people will say, yeah, of course, that doesn't make sense. Are you sure? Under what conditions is it right? Under no conditions. If someone says 1 equals 0, the theory's wrong. How about Einstein? If he says it, is he wrong? Well, show me where he says it. Okay, here's where he says it. Well, that's not what he means. Right? That's how the conversation goes. And so people do get into what one of my friends would say, denial is humans' favorite self-defense mechanism. And I think we see a lot of that for things that are sometimes somewhat obvious.
I think the one thing that has happened in the last 4 or 5 years, even politically, which I think is even helping science, is people are realizing what you are told by people in authority isn't always true. And we've seen giant examples of this, weapons of mass destruction held by a country and therefore starts a war. And then we find out there were none. And I'm not here to discuss politics. You just start to think, really, what's going on? A good example, of course, is Cynthia Whitney. She got her PhD in special relativity. She got her PhD in that at MIT. So if you want to have one of those people who are in a position of authority, she had it. And the first thing she got to do was to apply it to a real world problem of a ring gyroscope, which happens to be what's called the Sagnac effect. And it failed miserably. And she went back to her professor and said, I just applied all my work that I've done here at MIT to a real world problem and it failed. And you know about this? And the professor says, yeah, we know. But so what do we do? Well, there's not much we can do. And again, they're putting what I've heard from so many scientists is putting food on the table, right? This person has been there, they've had their tenure, you've listened to this, you've talked about it, you love it. The moment you have to question what you've believed all your life is something very, very hard. And I'm not sure if people can learn that or if you're just born with it and you've got it or you don't. And that's a real good question. I've got people in the green room. Is anybody in the green room would like to say anything? I know we've got a couple people. Oh, we got Ian Cohen. So, Ian, how are you?
Very well, thank you, David. Thank you, Stephen. I just had a question which is prompted to a certain extent by your comment about the ring laser there. I noticed, Stephen, that you quote, as Michelson Morley do, the orbital speed of the Earth of 30 kilometers per second, with respect to which we're measuring. But you don't quote the rotational speed of the Earth, say hundreds of meters per second typically, because there seems to be an asymmetry between the two. The former is largely mitigated by what might be conceived of as an entrainment, an ether entrainment, whereas the other shows up in experiments. And indeed, in an MMX type experiment by Bryant and Hall in 1979, the hundreds of meters, the 500 meters or something in Colorado actually showed up. So I'm wondering if you have a comment on that, or is that something you just omitted because it was another detail?
So I'm not as familiar with the later work that you just mentioned, but when you go back to the original Michelson-Morley paper, their data is I'd say that there is a question of is it going to be precision or accuracy? Let's see, it's probably going to be precision. So there's a question of precision, because they're measuring things and they're turning a dial and they're measuring it by hand. So there's some amount of error that does result in that. Not enough to discount their results, of course, but there is some amount of error. If you look at mathematics and computer science and how we evaluate different equations, there's this idea of big O notation. And big O notation says when you look at a series of equations, there's going to be one term that dominates. And so when we look at Michelson-Morley, the term that dominates is really the speed that we're orbiting around the sun, which dominates more so than the speed at which the Earth itself is rotating. I'd love to see newer data and see how that works with my equations, to be honest. It would be interesting to take a look at. So if you have any links to papers and those papers either have their data or point to a repository of their data, I'd love to take a look.
Yeah, the Bryant and Hall experiment of 1979 would be a good example for that, because the original MMX, which I suppose you were talking about, was not sensitive enough to evaluate or to show up any effects owing to the the revolutionary speed of the Earth. But it did show, it did have the precision to show any differences in the other speed, and it does actually show a cyclic variation, which you know about. So that's interesting. Actually, the Bryant Hall experiment that I referred to was actually analyzed later by Aspen, because they got the 17 hertz, I think, signal, and they said, well, it was just spurious, it doesn't make sense. But he analyzed that and he found that it actually referred to the revolutionary speed of the Earth at the location where the experiment was undertaken, which was in Colorado. I think it was something like 500 meters per second.
Yeah, interesting. And you can see that if you look at the equation. So again, just thinking of the bus example, which the jogger is undergoing cyclical behavior, right? And so if you just think of that repeatedly, you get cycles, right? And you could measure the distance and you could then convert that to wavelengths. So it's a pretty easy transition to go from what we talked about today to that. But when the bus is stationary, the jogger's cyclical length in both directions are the same. So you have symmetry. When the bus is in motion, then the length that the jogger runs from the rear bumper to the front bumper is longer than the length that the jogger runs from the front bumper to the rear bumper. So you still get the cyclical length with respect to the jogger's motion on the bus, but the length that he runs from in one direction is longer than the length in the other, and we get that asymmetry that you're talking about.
Okay, thank you very much.
Mm-hmm. Thank you for the question.
Okay, got some more questions here. Bill Howell, he says, question for Bryant, again from Edward Dowdy Jr. Any comments on the bending of light by plasma atmosphere versus claims of GR?
I don't know. And Ed and I used to have a lot of talks at conferences. And so, a great guy. And I think we had some conversations. I can't say that we got very far in trying to see if there was overlap between what he was working on and what I was working on. So I can't really comment on his work.
Yeah, it's unfortunate he just passed away recently.
Right.
I think at Alice. Oh man, it's tough to see that. Just really brilliant, amazing people. Having been involved with this over 30 years. I've got some questions here. Are you an etherist? And I'm not here to say because I'm not, but it doesn't matter because I believe it's a viable theory. But I was interested. It's sort of related to the question of why C is involved at all. Why do we always get this fixation of C and these movement? Because if you look at what you're doing, is it really related to C, or I don't think it necessarily is. Isn't it modern mechanics? Who cares about the speed of light? It's all moving things. Isn't that correct?
So in modern mechanics, I do look at the speed of the jogger. And in this case, you could ask, what does C represent? And so it could represent the speed of the jogger. It could represent the speed of sound through air. It could represent the speed of light through a medium. It could represent the speed of a swimmer through water, or the sound through water, or light through water. So C allows us to vary whatever we're looking at and take into account the medium through which it's traveling, or the velocity of the velocity of the object, or the velocity of the propagating medium. So there's different ways that we can look at what C means, but that's a good point. So in most of my derivations, and if you look at my derivation in my book, Disruptive, I don't use C. I actually use W for the propagating speed of the wave, the oscillating system, which it could be the oscillating system as a particle, or the propagation speed caused by that particle through a wave medium. But to associate it to Einstein's work like we did today and kind of make it clear that the derivations are in fact similar, I use C and I use the name Charlie, so that ideally people don't treat it as Charlie is running at the speed of light, which is not the case. Charlie's running at 6 miles an hour. And if Charlie's going to get to the front of the bus cannot go more than 6 miles an hour, because if it goes 7 miles an hour, which the bus can do, but now Charlie can't do what we've asked him to do, which was to oscillate. And that's the distinction.
That is very interesting. It'll take me a while to, that's fascinating to me, how that can be decoupled. And so my understanding is correct. C is interesting, and you can put it in there, but you don't have to. The system is the system. Mm-hmm. And I think one of the problems, I don't know if you feel this too, but one of the problems Einstein got into, especially with special relativity, is that there's this fixation everyone has on the speed of light. And because it's so fast, and that time slows down, length contracts, all these kinds of things. But it all, as you get close to the speed of light, your work is divorced from that. It's looking at systems in movement, and it's also, just to be clear, I just wanted to get it from you, it's totally Newtonian, correct?
It's totally classical mechanics based. So, yeah. Now you raise a really good point, and it's one if you remember at the introduction, you asked me how I got into this, and it was because we wanted to come up with a product for a company that would communicate faster than the speed of light. So that way, if you sent someone on a mission to Mars or to Pluto or whatever, you could talk to them in real time, or you could control that spacecraft in real time, which you can't do today. It's not going to be in real time. So that would require some sort of communication medium faster than the speed of light. So if you look at modern mechanics, because c is allowed to vary, if we were able to discover some communication medium that goes faster, and there, Van Flanderen, I think is his name, Van Flanders. There's another,
Van Flander,
Van Flander is another person who believes that there is such a medium. Then it works with this this model, because then all we have to do is say, well, what's the propagating velocity of that medium, and we're not limited to say the maximum of anything is c. It is, if you're talking about light in a vacuum, sure. But you can talk about other things that aren't light. Like I said, you can talk about a jogger on a street. You can talk about a fish in water. Well, be specific. Sound in water, light in water, me swimming through water, right? All of those we can be very specific about. So it's going to be something through a medium. And again, we could find some sort of quantum medium. That's my favorite thing to say, where could we look? Boy, wouldn't it be great if we found a quantum medium that had propagating characteristics that were maybe 10 or 100 times faster than the speed of light? Just think about what we'd be able to do then, and the math would still work for that type of model, for that type of medium.
Right. In our model, we have particles that go faster. That is the Coulomb effect. Gravity at our level is caused by a particle. Gravity at the level of an atom is a smaller particle. It's got to be faster than the speed of light. It's by definition. Anything that curves and orbits caused by that. So in our model, we have a particle that goes faster than speed. How much faster, we don't know. That's one of the proposals. We were making the same statement the other day, and we have some. I mean, we know that it's there, but to get the actual speed, we don't know. And to make something like that, it's not an easy technical problem. But I mean, there you go, is one example of possibly being out there. I guess we are coming up to the last. Is anybody else in the green room there want to make a comment before we go? Tell me, what's the future for you, Steve Bryant? I know you've been trying to get published. That's always going to be something. In fact, there's somebody here that says you should go on somebody's YouTube channel. I'll have to go back and check out Gareth's channel. I guess somebody said, here it is. So may want to check that out. Getting the word out is always good. Now, what that means, I'm not sure. So if you can email me that, SRC, and I do thank you for the donation. You can make, those of you who don't know, if you're on YouTube, you can donate through Super Chat. All the money goes to the organization. It doesn't go to me. But to keep all these things going. So that's really, but tell me what you've got your book, it's out there. Obviously you want to get it out there more. What is tickling your fancy? I mean, it's not like my dad, who one time came to me in the middle of my making the documentary Einstein Wrong and said, "I'm done, Dave. I did my paper." And then 3 months later, I go to his office and he's working away. And I go, "What happened?" He goes, "Well, I found something else. I can't stop." And so I mean, imagine your mind isn't stopping on this, or has it? Have you come to the conclusion you're done? Or is this the end swan song and you're going into now artificial intelligence and this is now a passing fancy? Where are you?
Great question. Here's the thing about me and physics, and even me and AI, right? I think if you find something you're passionate about, it's one of those things that if you ever say, "I'm putting this on the shelf," at some point you pull it off the shelf and you realize you're just working on it again. You just naturally gravitate to it. And that happens with me in my physics work and in my AI work. And I might say, okay, I'm going to put it on the shelf. And the next thing I know, I'm typing up a new paper. And so it's one of those things that's always with me. The other thing is, even though I've been looking at Einstein's work for probably 2 decades now and reading his papers and trying to tease out every little thing, each time I read it, there's a new aha moment, because maybe I've learned something new. So for example, before in my book, that the mean I used to call subtraction mean equation, and that was Steve Bryantism. And someone could attack that and say, Steve, you've invented something there that's not traditional math, so we're not going to pay any attention to you. Well, what I found is that it's actually the incremental mean problem, and it's used widely in computer science and statistics, so it's not a Steve Bryant creation. And so I've rebranded it to be what it actually is called, the incremental mean, and we're able to now talk through it and in a way that will be accepted because it is an accepted equation with a clear derivation. I mean, if anyone's interested in the derivation, look at chapter 2 of Sutton's reinforcement learning book.
Right. Well, we have everybody's really enjoyed this quite a bit. Here's a guy, Jose Ruiz. He says, "Thank you, everyone. Thank you, David. Thank you, Stephen. It was really great to get you on here. I hope we can get you back when you do something new. If you have a paper you want to publish, we do have our conference coming up. Even if it's a short paper, I encourage people. You don't want to write a thesis paper that's taken 4 years. If I have a couple subjects I want to talk about, they're not big, but maybe thoughts that you think that people could be shared, and of course being published. But I want to thank you so much for coming on. I truly enjoy and truly enjoy talking with you. And again, your book is for sale. Is it for sale on Amazon around the world? Is that right?
Yes, David. So first off, thank you for having me today and hosting. I know you've been trying to coordinate with me for some time, and I apologize. I had a paper that I was trying to get published, and like I said, was recently turned down for having not completely read it, which is always interesting. But I understand why. One of the courses I've taken is a class in research. You can think of it as prep for a PhD program, and as part of that class, I've learned how people read academic papers. And as a result of that, I can say that when I rewrite my paper at some point, then I'm going to write it the way that I know people read it, and ideally maybe I get through a few hoops that way. But thank you for having me. The book is out there on Amazon and Barnes and Noble and things like that. You can get it in hardback or paperback. The equations didn't quite show up properly when I tried to do it as an ebook, so we quickly pull that down. But at some point, I may put an ebook version back out there.
I found a place. I think it was for a couple $100, and our book is tough. We got a lot of graphics. I mean, half the book is graphics. And for that $200, they'll go to eBook and they'll check it and make it flow, the whole thing. So I'll let you know about that because it is hard. I mean, I'm in NLP, natural language processing. I can convert anything to anything. I can get things, computers to read like humans. It is a tough problem. So maybe you want to do that because the ebook is always welcome. So maybe we'll get you to get that out there. But thank you so much again. Congratulations. Your work is just stellar. My brain is, every time I talk with you now, I'm going to be walking around for a few days thinking of joggers and buses and that. It's going to take me a while. Then I'll probably run into a wall or fall into some a hole while I'm thinking about it and not paying attention. But thank you so much and congratulations. I'm sure today a lot of more people got exposed to your work, and hopefully we'll be seeing more of your papers. If you can't get that published, you want to publish with us, one thing we do allow, you can publish it anywhere. You don't have to, you're not exclusive with us, so you can always republish. But thank you so much, and thank you for getting up so early. It was well worth the time. I think everybody enjoyed it.
Thanks again, David, and thanks everyone for joining us today. Really appreciate it.
Okay. Well, thank you so much. That was absolutely great. We ran a little bit over, but it's well worth it. Steve is an amazing mind, and if you do want to check out his work, check out his book. You can really read it, have it in your hand, go over it, take some time, but really brilliant man. Really, 1 equals 0, can't make it easier than that to show Einstein's calculations and wrong. But I want to thank him, and let's go out. And always, always stay critical, stay thinking. I'm Dave D. Hilster. I'm your science therapist trying to get you to the promised land of becoming a critical thinker, keeping your mind open to new ideas, because we don't all own the truth. In fact, all of us have part of the truth only. Ciao for now.